Okay, well, I'm just gonna get started. Um, so we're talking about autonomous today. Um, yeah, so it's a little bit of a longer presentation compared to normal, but hopefully y'all can learn something from it. So just in general, like what is autonomous versus teleop? So in autonomous, the robot's on its own versus in teleop when the robot's responding to human input. And the main difference is just how the robot is controlled. And this primarily affects how we write code because obviously it's different based on whether you want to have something pre-written versus whether you want to have the robot like reading in from a controller or something. And in FRC, obviously they represent different parts of the game, right? Whether it's the 15-second autonomous period at the beginning or the 2-minute 15-second teleop period. And sometimes they have different goals, so you have to keep that in mind in terms of scoring. And you'll have to consider the different starting configurations in auto, things like starting within frame perimeter, and yeah, so a few different things you have to consider when programming auto versus programming teleop. Other things to compare and contrast. So in autonomous, the only input you're getting is from sensors, while for teleop you have both user input and sensor input. In auto, it's generally little change in instructions. So every time you go out on the field, you want to like have it pretty much be the same thing. While for teleop, the instructions can change quickly because even if you're like about to drive forward, if another robot comes in your way or something, you want to change that right away. For the autonomous period, we more or less have known starting conditions, right? We know what game pieces we start with. We know where on the field we're starting. Um, we should know our robot starting configuration. But in teleop, like things can change at any time. You don't know when you're gonna pick pieces up. You don't know when other people are gonna get in your way, and your robot's like changing all the time. Um, Auto also has a relatively short runtime, both during and outside of competitions, because it's always like a short routine at max like 15 seconds, which you're going to run and then it'll end. But teleop, you need to kind of consider that it's running indefinitely when you're testing, right? You don't know how long you're going to be like practicing for, or and even in competitions, it's 2 minutes and 15 seconds compared to 15 seconds for autonomous. Um, the final point is that autonomous is relatively predictable. Like obviously you don't know if something's going to break or if another robot is going to go rogue and like get in your way or something. But generally, if everything goes as expected, you know exactly what's going to happen in those 15 seconds. And you don't really need to consider like adapting to things because normally there's no defense allowed. There's no like, random game pieces rolling around on the field. But a lot of those things you have to consider for teleop. So in terms of control flow, for teleop, you have the driver's judgment, right? So then they have drive input and also buttons maybe to complete actions or whatever, as well as sensors, which are normally used for maybe picking up game pieces, limit switches on things, and like we talked about last week, PID control. And then the code output for that will be motor speeds and piston positions, which are then turned into electrical control, like where to direct power or how much power to send to each component. Oh, quick question, Liam. Are you recording this?
Yes.
Okay, great. Yeah, so comparing this to autonomous, the main thing that changes is the input, right? Because the pre-written code is like drive instructions, the pre-planned actions, there's no driver input there. And also the sensors, in addition to the game pieces, limit switches, and PID control that you will normally have, you also have things like current motor speeds, so like encoders or whatever as well to read in that information. And you might be using sensors to figure out what your next actions will be. Um, but the output is still going to be the same. You still have motor speeds, piston positions as your output, which is then changed into electrical control. So again, looking a little more specifically at what happens in teleop driving, it's normally joystick input, which is converted to a target speed, and then that's converted to motor output. Versus in autonomous, where you have pre-written code, which gives the target speed for the motor output. Are there any questions? All right, I'll take that as a no. So just before we dive in, remember like when you're programming auto, like to be safe because a lot of times things can go unexpected and you want to make sure there's no humans in the way. You're not gonna like hit them. And also we've learned this the hard way, but robot mechanisms do not always act the way you want them to. And so you don't want to like you want to make sure that the robot doesn't bump into anything or break, and also try to make sure you have things like limit switches or at least be ready to emergency stop or like stop your robot so that you don't end up breaking things when you don't have to. Um, we also want to have some amount of adaptability. Uh, in we don't always want to like assume that things will go perfectly, which is why things like practice matches are really helpful in case the conditions during a competition are different from what you've like tuned your robot in terms of like the field or like lighting if you're using vision for anything. Um, there's also a lot more defined like actions and end goals for autonomous, and that plays in a lot of different ways. Like we like actually naming our um, different paths based on like what the end goal is or what actions it's doing, and that makes it very easy to go and maybe like talk to other teams about what autonomous you're doing and where you're going during that autonomous, and then kind of plugging that into your program and running the right code. And of course, the biggest thing about autonomous is consistency. You want to make sure it's always doing what you expect it to. Um, and so you're going to want to do a lot of testing and make sure that it goes exactly where you want it to go, does exactly what you want it to do, so that you're not showing up at competition and then nothing goes as expected because you didn't test it enough. So the first auto is the easiest to implement. It's basic single speed auto, which a lot of times in the games you can get a point for like moving across a line or just getting out of the starting zone or something. And so if you just set your drivetrain to a really slow speed in the periodic loop, you can just keep driving the entire 15 seconds, and that requires nothing to work but a working drivetrain. And as you can see, the code is very easy for that because you just need, in your loop, you just set your drivetrain to some slow speed, like 10%. If you want to get a little more refined, you can also do like a time-based auto, which can also earn those points for moving off the line or moving out of the starting zone. Um, but the difference is that you can stop. So if you're, say you want to like start somewhere where you'll hit something after a while, or want to make sure that you don't go into the opposing alliance's territory, then you can do like check the certain amount of time and then stop. And the only like added, I guess, issue with this is that you have to test and make sure that your robot like goes and stops at the correct distance, because if you're just guessing the time, you don't know where it'll end up. But if you test it beforehand, you'll know like, okay, it's going 10 feet in 5 seconds, and so maybe we should like change that time or whatever. And the other benefit of that is that you can add other robot actions at the end too, because then you can say like drive forward for 5 seconds, and then once you stop driving, like eject. And so we can have really basic autonomous paths like that. The code's a little more complicated, but basically, since you can't use a while loop in robot code because of the looping, you just want to start by when in your initializing. Kind of have a variable and mark down the start time. And then, yeah, so once you save that start time in your periodic loop, you just keep checking whether your current time is equal to the whatever you want the elapsed time to be. So in this example, we have it as 10 seconds because in Java, this is for milliseconds. And then while you're less than the target time, you keep setting your speed to a certain output, so 25% in this example. And once you've reached that, you can do whatever you need to do to score and make sure you set your drivetrain to 0. Okay. And then the next one is called Dead Reckoning, which is basically a series of steps with instructions for driving, turning, or other actions. And it's basically uses encoder inputs and angles from the gyro to kind of figure out like how far the robot's moved or turned, and then using that to kind of, whether it should keep going or whether it needs to stop and move on to the next step. And so, of course, compared to the last two, this allows for more complex paths. You can have turning, which is also generally more reliable than time-based auto because you actually know where your robot is versus just you trying like relying on the time that has passed. Um, but it's not necessarily the most efficient paths because you can only like it's more difficult to I guess turn and drive at the same time. Um, and it also builds up error over time. In any auto, you're gonna see this where if you keep running it, like every time, the wheel will slip a little bit or the gearbox will slip a little bit, and then that error adds up over time. And so you know, running a path for like 10 seconds versus running a 20-second path, you'll be more off when you're running a path for a longer time. But I think in Dead Reckoning is one of the most like difficult ones to run in terms of error because if you're always counting on the encoders to know where you are, like the first time you say move forward 10 feet, but it only goes 9 feet, and then it turns like 90 degrees, but it only turns 80 degrees. So all those little errors kind of add up over time so that you end up like farther and farther away from where you're expected to be each time.
Yeah, like the one thing about this is if you have an inconsistent drivetrain, like if you have one chain that's super tight on the left side and super loose on the right side, it's gonna compound these errors. So basically, whenever you're working on auto, try to have a, the best drivetrain you can, because this is where the errors really show up.
Yeah. Yeah, so here's just a quick example, kind of based on some Dead Reckoning code from our team a few years ago. So they had a method called auto forward where you feed in a speed and a distance. And so it just keeps checking the current distance that it's at based on the encoders. And as long as that's less than your target distance, you'll keep setting the speed. And this will also include an adjustment for the angle because, again, like Liam mentioned, if you have a chain that's tighter on one side, then your robot like when you put like full speed forward on both sides it might end up like driving to the side, and so you can use the gyro to make sure that you're still driving straight, which can actually end up looking pretty funny because if you start turning and then you have to correct yourself again, which also adds to the error of this method over time. um, but yeah, you keep setting this, and then once you reach your target distance you can just say okay, we're done with this step, you can move on to the next step. Similar thing with turn, where if you send it a target angle, and as long as your target angle is not, or your current angle is not equal to your target angle, you turn towards the target angle. And you can put this all together to make different paths, which is probably a lot easier than trying to time something out. Like in this example, we go forward at half speed for 14 feet, turn 90 degrees, then go forward at quarter speed for 3 feet, and then do the gear place action, which is another method from this. Are there any questions about those three?
No.
All right. So one other auto thing I'm gonna briefly mention is like a recording type of thing. I don't think it's very widely used. I'm sure there's other teams out there which do it, but we used this in 2018 because we didn't have encoders on our final gearboxes for the robots, so we used this method, which kind of records the drivetrain speeds while you're in teleop. So we would have the driver like kind of drive out a path, and then we would write to a file the joystick input. So during auto, it then plays back this recording by feeding in the motor speeds from those files. And so it's basically just mimicking teleop driving, but as we were talking about this before, it's kind of inconsistent. We found that it wasn't always playing it back and at the same speed, so it would end up at slightly different positions each time. And also the other issue with this is that you cannot modify it and you can't really optimize it. It's only what your driver did in that one time that you're playing back, which you can do. And so if you have to change even a minor thing, you have to redo the entire um, recording of it. And finally, the one that I'm going to talk about a lot now is called trajectory following, because it's the most complex, but it's also really reliable. And you generally use an existing code base, so you don't have to really understand what's happening. Like you don't have to understand every little detail because there's a lot of different implementations out there. Like WPA has one. I think there's one called Pathfinder. Yeah, so lots of options out there. Um, but in short, what you do for it is you give a position and headings for different points on a path. So you would say start at 0, 0, 0, which is x is 0, y is 0, and your robot is facing forward. And then say you want to move 10 feet forward, 10 feet to the right, and then you have your robot be facing to the right, then your second point would be 10, comma 10, comma 90. And so what trajectory following will do is it will generate a trajectory, um, which will be split into small pieces with its associated left and right speeds. And then your I guess there'll be like a following code which runs those speeds on the robot, and then it'll follow that trajectory that it generated and get you to that final point or get through multiple points if you have multiple points. And so here's like a picture showing that. If you start over here with the robot facing this way. You want to go through this point here with your robot facing this way, and you want to end over here with your robot turned. And so this is what it'll generate, is this path here. And then it'll split that up into left and right speed so that you can actually watch your robot drive that path. So it starts with the waypoint pair, which is that the three the x and the y and the heading, which you plug in, and it generates a mathematical equation to represent that path. So this is a function of time, and it's a polynomial of some degree, and it's normally cubic or quintic, because if you had it, so that just means that your highest terms are either something x cubed or something x to the fifth, and you use those instead of like squared or to the fourth, because then you can have the curves like coming kind of around or like turning in on itself. And the code which you use, like from whatever library, will calculate the coefficients for these polynomials and generate that curve which goes through the different points that you said you wanted to go through. So for each pair of points, so like in this example, there's 3 points. So the code will take this point and generate either a polynomial with x cubed or with x to the fifth, and get this part of the curve, and then you can do the same thing for these curves here, or these 2 points here to get this curve, and then it'll put it all together to get this whole curve. And yeah, like if you look at this one closely, you can kind of see how it looks like an x cubed or x to the fifth function that you would graph. And yeah, this is known as a spline, if you want to get more technical terms. And again, this, you don't need to know this super well, but it's helpful to know that some of the trajectory generation code, some of them use calculus, which uses the small changes in x distance, y distance, and angle to make that arc and split it up into the different like the different, I guess, speeds for each point on the arc. Or it can use motion profiling, which basically uses the robot's maximum acceleration, maximum velocity, and a few other parameters to calculate that arc. And we'll go more in depth on that next week. But either way, the end result is what you care about, and that's a generated path which has robot velocity and acceleration at every single point along that path. But now you have to convert this robot velocity acceleration into values for each wheel, right? Because like when you want to turn, for example, one side will be going slower or the opposite direction as the other side. And so the the trajectory generator you use will have like physics equations with it to convert it into those individual speeds for right and left. And then the final part of the code is where it takes out those wheel velocities and uses just a basic P proportional controller on each side of the robot for the wheels. Another small point is odometry. So that's basically using the encoders and the gyro to track your position and angle on the field. And some followers use this information to adapt if the robot goes off the planned path, right? So if you're supposed to just go straight, but the encoders can tell that you're being pushed or being turned in another direction, it'll adjust the use the P controller and adjust the velocities to get you back on track. And yeah, again, like we said with the Dead Reckoning, odometry isn't super accurate because of error that can build up, friction, those kind of things. It's useful, especially at first, it can be pretty accurate, but over time, again, the error is going to accumulate and it's not going to know as accurately where it is. So, in summary, like the main points for trajectory is that you input coordinates and headings for different points on the path that you want the robot to take. And you also plug in some velocity and acceleration constraints so that it knows how fast your robot can accelerate and how fast it can go. And you tune a few other parameters like the coefficient for the P controller on the wheels. And then the path generation code will create an equation for the path based on the points that you plug in. It'll find the different robot speeds and accelerations over time on that arc, and then it'll split that into left and right speeds and accelerations to feed into your robot and have it drive that path. And so we have an example here of how it works for us. If you can see the GIF, it works like pretty well, super consistent. And we also had our vision here to make sure that even if we were slightly off, we could still get it in. And as you can see, like once we implemented all the code, it's actually like super simple to write. We just add like all these actions to our scheduler, and then like here's one part of the path. We just have to say like add these two positions because we want to start at wherever we are, go 14 feet forward, no change in y and no change in angle, and then it'll add that trajectory there, and you can see it driving in this first part here. That's the path. And then the second path here is driving, starting at the second point here and then driving back and then ending at a slight angle. Okay. Questions? No, that was a lot.
Um, is there like a way to like fix or like correct the errors that happen when you're how you're explaining the errors that happen over time? Is there a way to do that as you go along so that's not as like visible?
So
Yeah,
there
you
you
want
go.
to say? No, you go ahead.
Okay, so what you can do is, this is not like commonly used, but whenever you see a vision target, you can calculate how far you are from it, and then re-zero your odometry there. And so basically, as long as you see a vision target, you can correct for like compounded error. But without vision targets, it's pretty hard because you have to account for wheel slippage, which is basically impossible to account for.
Okay.
Any other questions?